So let me explain that. Right. Okay, the problem statement what I gave is px minus y py plus x equal to a square p. A square p, yeah. Px minus y into py plus x is equal to a square p. So this is the problem statement what I gave. And this actually reducible to Clairaut's equation. Right? Suppose let us introduce new variables. U equal to x square and v equal to y square. And du by dx is equal to 2x and dv by dy is equal to 2y, right? And if you take the ratio, so this is du by dx divided by dv by dy, and this can be treated as du by dv into dy by dx is equal to du by dx value is 2x and dv by dy value is 2y, and these two will cancel, and then y by x into dy by dx is equal to dv by du. Got it? So we have just introduced u is equal to x square and v equal to y square, and from there actually we have got y by x into dy by dx is equal to dv by du, and we know that actually small p, so small p is equal to dy by dx, or if you replace q is equal to dv by du, if you replace with q, then actually we can establish a relation between these two, that is, so p into x by y is equal to q, right? So p is equal to x by y into q. So this relation actually you can replace wherever p is there, that is x by y into q minus y into p into, so p is x by y into q plus x is equal to a square into x by y into q, right? And this y will cancel, and so this is xq minus y square whole divided by y, and this is x you can take out common, and this is q plus 1 equal to a square q into x by y. So this x will cancel, this y will cancel, so we are left with xq minus y square okay, xq minus y square into q plus 1 equal to a square q into q plus 1 equal to a square q, right? And this is xq square minus y square q plus xq minus y square equal to a square q. Yeah, so this is where it is missing. So px, right? So there is x by y into q is the value of p itself. There is one more x. So this was missing. I hope you got it, right? So let me explain again. See this, actually we have got the relation y by x into dy by dx is equal to dv by du, and p is equal to x by y into q. So where q is dv by du and p is dy by dx. So until this point, do you have any questions? Yes or no? Make it fast. Right? So until this point, actually everything is clear. We just substitute u is equal to x square, v is equal to y square, and from there actually we tried establishing the relation between dy by dx and dv by du. And if you assume this as p, that is dy by dx, and dv by du as q, then actually we can get the relation. The small value, small p is equal to x by y times of q. Now actually we will replace this value in this equation, the original differential equation, in terms of q, that is px. So x into p value is this entire thing. So that is x by y into q is the value of p, minus y into p is again x by y into q into y plus x. Now actually this we can simplify it further. So this becomes x square, x into x, which is x square, and then actually so LCM minus y square divided by y, and in this y cancels and x is common and q plus 1 is left over, and this value is x value will cancel out, y value will cancel out, x square q minus y square is into q plus 1 is equal to a square q. So this is x square q. So x square q, right? And x square value is u. So u q minus y square is v. So v q plus 1 is equal to a square q, right? And then so this u q square minus v q plus u q minus v equal to a square q. And so from this what we can do is, or else actually we will just multiply with v. So uq square plus 1 uq minus v into q plus 1 equal to a square q. Right? I just multiplied with q, so that is uq square minus vq minus vq, and then actually I multiplied with, so uq minus v, or uq into q plus 1 minus v into q plus 1 is equal to a square q. Now this is what we can do is v into q plus 1 is equal to uq into q plus 1 minus a square q, and this is v is equal to uq into q plus 1 divided by q plus 1 minus a square q divided by q plus 1, and this q plus 1 will cancel, so v is equal to uq minus a square q by q plus 1, right? So this is the differential equation. Actually finally we have arrived. So in this case actually, do you have any questions in this derivation? Yes or no? Is there any confusion in this derivation? So I just actually replaced dy by dx value in terms of du by dv, and dy by dx actually we assumed that this is going to be p, and du by dx, dv by dx actually du we assumed this as q. And this way actually we just replaced every value and we brought it into this particular format. And finally I expressed in this format, that is v is equal to uq minus a square q divided by q plus 1. So don't you see that actually this equation is of this particular format, px plus f of p, right? So that is, instead of y now it is v, instead of x now it is u, and instead of p it is of q. So don't you see that 1-1 correspondence between these two? Yes or no? So I hope everybody understood this. So finally actually by introducing y square is equal to v and x square is equal to u, we were able to bring the differential equation in the Clairaut's equation format. So this is the Clairaut's equation if you notice. So y is equal to vx and px plus f of p format. So this is the Clairaut's equation. And this Clairaut's equation, we can find out the solution straight away by replacing q is equal to c is the solution directly. So we can simply replace the general solution is v is equal to uc minus a square c by c plus 1. A square c by c plus 1 is the solution but u is x square and v is y square. And this value y square is equal to u square, so x square c minus a square c by c plus 1. So this is the general solution. So we brought in the form of the Clairaut's equation and we just replaced it with the original values, x square, y square values, and also the constant value. Got it? Any questions? Any questions on this? Right? So can you try to identify the singular solution if exists for this? What about the singular solution? You can use the C discriminant format, right? Right? So if you wanted to identify the singular solution, so x square into c plus 1 into c minus a square c is equal to y square into c plus 1. So this is x square into c square plus c minus a square c equal to y square c plus y square, right? And x square minus y, so x square c square plus x square c minus a square c equal to y square c plus y square, right? And so c square term is only here, so x square c square, and c term is here, here, and here. So this is x square minus y square minus a square times of c, and that's it, right? Yeah, in every term actually, so there is a constant term also. Minus y square equal to 0. So this is the C quadratic equation, right? Now this C quadratic equation, we can identify b square minus 4ac, that is x square minus y square minus a square whole square minus 4ac. So 4x square y square equal to 0, right? 4x square y square is equal to 0. Now this actually we will have to simplify to identify the singular solution. So you can expand it and then do that, or else actually you can leave it as it is, right? So from this actually you can identify the singular solution. In the statement it was not asked for the singular solution, but this simplification leads to the singular solution. Got it? Understood? So this actually you need to expand it, a plus b plus c format, and then actually simplify it further and to identify the singular solution. Also actually you have to prove that whether this satisfies the original equation, then only we can call that as a singular solution, otherwise it's not, right? So I hope you got a fair clarity on this higher degree differential equations of first order. If you have any questions, you can ask me now, or else actually we can move on to the linear equations. Clear? Right? And the next concept is the linear equations. So first actually we will deal with constant coefficients. So earlier actually we already discussed the linear equation. So the linear equation standard format is, suppose dy by dx plus p of x into y is equal to q of x. So this is actually the first order linear equation. Right? So this is the first order linear equation. And now dy by dx plus p of x into y is equal to q of x, which is the first order linear equation. Now in this actually what we are doing is, here there is a variable coefficient that is going to be present. And if this is also a constant, suppose actually if the differential equation of dy by dx plus y is equal to q of x, and this is what we call as the width. So it can be a, it can be b like this. Then this is the linear differential equation with constant coefficients. Linear differential equation with constant coefficients. Right, with constant coefficient. Now, so this is the differential equation we were talking about. Now, if you try to understand carefully what exactly it means for us, usually any differential equation will always consist of two different solutions. One is the transient solution and the steady state solution. Right? So I should be giving the physics background around this particular differential equation solution so that actually you can appreciate what exactly we are trying to solve. And if you notice, actually in the first order differential equation, actually we will straight away identify the solution of this differential equation with the normal Leibniz method. But what about if you give the differential equation, so here d square y by dx square plus b into dy by dx plus c into y is equal to f of x. I think actually in your engineering or in your graduation, you might have solved this kind of differential equation, even with higher order differential equations. But while doing the solution, you might have noticed that actually the complementary function will be found separately and the particular integral will be found separately. I hope you know that, right? Right? So why actually we have to be doing in that way? That is the fundamental question. Because in the first order differential equation, there is nothing like the complementary function and the particular integral. We are straight away identifying the solution. Then why we have to separately discuss in the context of the in the context of the higher order differential equations only? That question needs to be answered so that actually we can proceed further. So for that actually you need the physics background. Now let me explain. Suppose if I have an RL circuit. So these basics actually whatever I am going to explain. So is actually very fundamental and most of the people already knows this. Now irrespective of your background, whether you are graduation or electrical engineering or electronics engineering or mechanical engineering or any kind of stream it is, you might have noticed this kind of circuit. Let me explain what exactly it is. And this is a resistance R and this is an inductor L, right? And there is a voltage source of V here. Now, as per the Lenz's law, which says that the voltage across any inductor is always L di by dt. So the rate of change of current that is going to be flowing in the inductor will decide how much is the voltage drop across this. So the value is going to be practically equal to L di by dt. Now, if you try to solve this differential equation, or actually if you try to identify whatever the current that is flowing in the circuit, and for that actually you will use the Kirchhoff's voltage law, which is the voltage across this resistance, voltage across this inductor is exactly equal to the voltage that is applied, right? So this is what we call the Kirchhoff's voltage law, which says that the voltage across the inductor is L di by dt plus the voltage across the resistance is I into R as per Ohm's law, and the voltage that was supplied is V, which is a constant value. Now, don't you see that actually this is a first order linear differential equation, right? So this is actually dy by dx and y. So I value is actually y and this is the constant. So here p of x is simply r by l and q of x value is v by l, where both are constants. Got it or not? So this is actually where both are constants in this particular case. So this is actually the first order Leibniz equation if you notice carefully. So di by dt plus I times of. So if you notice one di by dt is there, one I is there, and remaining values are functions of t, or actually a function simple constant, which we can call this as the Leibniz equation straight away. Then we can identify the solution for this. So I into the integrating factor is e power. So first we will calculate the integrating factor. So e power integral. So r by l into dt. So this is e power rt by l, and this is the integrating factor. So I into e power rt by l is equal to the right side value is v by l into integrating factor e power rt by l dt plus c. So I into e power rt by l is equal to v by l e power rt by l divided by r by l plus c. So this l will cancel. So finally we got the solution. So I into e power rt by l is equal to v by r times of e power rt by l plus c, or this can be treated as v by r plus c into e power minus rt by l. So this is the solution actually what we are going to get it in case if you solve this particular differential equation. Got it? Right? Now if you notice this particular solution, if you carefully understand, I'll just actually rewrite this. So I is equal to v by r plus c into e power minus rt by l. And if I separate this solution, v by r separately, c into e power minus rt by l separately, if you separate it, there is one portion of the solution which is purely dependent on time. So this is depends on time. And this is independent of time. So this is independent of the time. So there is certain portion which is dependent on time. There is certain portion which doesn't depend on time. And also, if you carefully notice, as t tends to infinite, it loses its influence. Correct or not? As t tends to infinite, it loses its influence. And here, it doesn't matter whatever may be the value of t, it is always v by r that is going to be maintained. So it loses importance. With time. So as time keeps on increases, it loses its importance, because when t keeps on increases e power minus infinite, it will become 0. So this portion completely will be eliminated after certain amount of time. So this portion of the solution is called as the transient solution. So transient solution which is dependent on time, and over the time actually it loses its importance, right? So this is what is called as the transient solution, and this is the steady state solution. So in our mathematical terminology, this is what we call as the particular integral. And this portion actually we call this as the complementary function. Right? I hope you understood this. So the complementary function and the particular integrals are nothing but the transient solution and the steady state solution respectively. Now that's what exactly is happening here. So is this understood? Irrespective of your engineering background, this you should be able to understand. I made it simple. Yes or no? Right? Okay. And the next important point you need to understand out of this solution is, see this, if you notice, this is V. And here there is a R value, there is L value, and this is an arbitrary constant. And here V has a special importance. Let me tell you what it is. Now see this, out of this circuit, this is actually the designed circuit where you don't have the control once it got designed. But the external input, actually the voltage that you wanted to supply has your own control. So that is, you can apply 10 volts, you can apply 100 volts, you can apply 1000 volts. That depends on your interest. So whatever may be the voltage you are interested, you can apply it. But once the circuit got designed, it will not be changed at all. So because this is finally black box, you don't have any control into the inner elements. But external terminals, you can apply any voltage, whatever is interested for you. So this is the source. So source function. So this is the source function or input function. And this input function usually, if you notice in our differential equation, this is on the right side. Right, in our differential equation, that is on the right side. But the left side portion, if you notice, that is purely the circuit elements that are going to be there. And the circuit elements, that is the R value and L value, will decide the left side portion, and the right side portion actually is purely dependent on the external input or the source function, whatever you are going to inject it. Now, if you notice, whatever the source function you are giving, that is the finally deciding factor. So if you notice in the final solution, so here after a certain interval of time, actually it will be losing its importance. This portion actually finally it is deciding the current. So final current or the final output value you are going to see is the V by R value. That means the inductor element completely loses its importance because actually it is dependent on time. And here the transient portion actually it will have a huge impact during the initial time. So the circuit elements, if you notice, the basic nature of the inductor is it will not allow the changes of the current through it. That is the reason what happens is initially when you switch on, suppose actually if there is a switch over here and this switch actually it is open and now actually you wanted to switch on. So if you switch on, suddenly the current wanted to increase. So how it wanted to increase? As and when you switch on at t equal to 0, it actually horizontally wanted to raise it. That means the same amount of the current actually it wanted to maintain once the switch is on. But when you start counting it, it has to be started from 0 and it has to raise to 100 value. So that is, if it has to raise, definitely it will take certain amount of time. So this portion of the time, it will use to raise the current, because minimum certain amount of time it has to be there to raise the final value. So it will be raised till this extent for a certain amount of time, and after that actually it will maintain the same constant value. Now from here onwards, actually this is the V by R value which is going to be maintained constant, but initially this inductor will be dominating, so it will not allow to change the current. That's why actually it will try to act as an open circuit initially, and slowly actually it loses its importance and finally allows all the current, and it loses completely its importance and it will act as if like normal short circuit after the time gets over. So maybe after 1 hour if you check it, it is as if like a simple wire, it won't act as an inductor. So it is the V by R value which will be the final current actually which is going to be flowing. Got it? I hope you understood the concept. Right? Now what I wanted to tell here, it is here the circuit elements will be dominating. Will be dominating. Right? And here, from here onwards, source will be dominating. Right? So initial times actually the circuit elements. So in this black box, whatever is there, that will have a huge impact initially, and outside the black box, whatever is there, that will have the impact permanently. So both together actually will decide how much is the current that should be flown within this particular circuit. And this kind of analysis, not just for electrical circuit, irrespective of your engineering field, maybe mechanical engineering, maybe civil engineering, maybe chemical engineering, maybe metallurgical engineering. It is the same scenario actually, it happens everywhere, exactly 100% same. So suppose actually if you talk about the motor, then actually, so the motor actually it has to be driven, right? So electrical input actually that will be given and motor will be driving. Suppose actually if a motor drives the generator, the mechanical input is the source function there. Now the circuit elements here actually, we have the circuit elements in the case of electrical engineering. But if you take mechanical engineering, the bearings and the weight and the moment of inertia, all those elements actually once it was designed, it was fixed. But how much input you are going to give it to that, that is an external input. So with what torque you are going to drive, so that is an external input. So the external input actually finally takes the control. But initially, when you switch on any particular motor, initially it starts slowly and raises. Even if you start the car, so you will always keep it in the first gear to raise. Once it was raised, then actually all the moment of inertia, everything actually, it will be losing its importance. Finally, the car speed actually is decided by the how much fuel you are going to inject it. So that is the external input, that's what you are going to do it. So even if you model a mechanical equipment, it exactly resembles the same differential equation. There will be a source function and there will be the circuit element components. So the components actually will be having a huge impact initially. That is, the first gear you will be using only in the so when you are starting, or actually when it is very, very slow, where the circuit elements or the mechanical equipment of the car will take the control. But once actually it was raised, then actually you are going in fifth gear, then actually the fuel, how much you are going to inject will decide your speed. Got it? I hope you understood the context. Right? Now, based on that scenario, any differential equation, which is the model of any physical problem statement, will always be divided into two different portions. The left side portion is purely dependent on the circuit element. The right side portion is purely dependent on the source portion. And source value will finally decide the value. And initially it will have a huge impact, this one. So the solution alone this, so this is called as the transient solution. Because initially it will have its impact. Transient solution, and in our normal terminology, this is the complementary function. Right? And the right side portion actually, this is what is the final. So this is the steady state solution we call. Steady state solution will be decided by this. Or actually I'll put it in the next slide. So that is di by dt plus r by l into I is equal to v by l. And the right side portion actually, the steady state solution or the particular integral or the final value will be decided by this. And this portion, the transient solution or the complementary function or the initial solution will be decided by this. Right? So because of that reason, we will be calculating the transient solution separately and the steady state solution separately. But in case of first order, first degree linear differential equation, we have got an advantage to get the complete solution together. So with the help of the Leibniz equation, we can get both the solutions together. So that is the only advantage. So in case of first order, first degree differential equations, we can get the steady state and transient solutions together. But the same is not possible with higher order differential equations. Because in case of first order differential equations, we have got the advantage with the help of the Leibniz equation. Straight away, it will give the sum of both the solutions together. That's exactly what we have derived. That is, we have derived this equation v by r and c into e power minus rt by l. So this is the particular integral portion and this is the complementary function portion and this is the complete solution. Got it? But the same thing actually is not possible in case of the higher order differential equations. Now actually we will solve that separately. How we are going to solve it? So see this, suppose if I have this a into d square y by dx square plus b into dy by dx plus cy equal to f of x. So this is the differential equation. Now this is the source function. And this is the dynamic function. So this is actually, we call this as the system dynamics. Now, so the complementary function is the one when there is no source, how exactly it behaves. So that is exactly what we call as the transient solution or the initial solution. So when there is no source, how it behaves. So when there is no source, the response is purely due to the system dynamics. Purely due to the system dynamics. So that is the reason when we solve the complementary function, we take a d square y by dx square plus b into dy by dx plus cy equal to 0. So making source 0. So if I make source 0, then it will be purely the transient response. So the value of y is purely due to the transient response. Right? But in case of the particular integral, the final value of current, even the circuit elements also will decide along with the source. If you notice, in our analogy, So finally, V by R is the value which will decide the final current. V is the source function, but R is the circuit element. So along with the circuit element and along with the circuit dynamics, the value of V will decide the final value. So R is also part of the circuit element and even in the final solution also. So that is the reason when you calculate the particular integral, we will be calculating AD square plus BD plus C operated on f of x. So here the circuit element cycle will make the role. Got it? I hope you understood this. Right? So both together, that is the complement. So once you solve this one, this is what we call as the complementary function, and we solve this and we call this as the particular integral. The general solution is said to be the complementary function plus the particular integral. Got it? Understood? Any questions? Any questions on this? Right? So this is the entire physics background in handling these differential equations. So why we will be doing this complementary function separately, particular integral separately, just because of this fact. So we have used this physics terminology and we were able to arrive the solutions based on this understanding. Clear? Any questions? You can ask me now. So once you understand the concept, then we will go into the mathematics, right? Okay. Now, so we understood actually why we will have to divide the complementary function separately and the particular integral separately. And based on that understanding, actually, first we will discuss how to calculate the complementary function. So first, actually, the linear differential equations we will discuss. Right. So any equation of the format right, an d power ny by dx power n, an minus 1 dn minus 1 y by dx power n minus 1 dash 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 a dy by dx plus a naught y equal to f of x, right? And this equation actually is called as, so this kind of equation is called linear equations. And the next one is, if a naught, a1, a2 dash 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 an minus 1 an are constants, then the differential equations are said to be linear equations with constant coefficients. If a naught, a1, a2 dash 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 an minus 1 an are functions of x, then the differential equations are said to be linear equations of variable coefficients. Right? So this is the definition of the linear differential equations, and we have actually the linear differential equations with constant coefficients of this particular format, and the linear differential equations with variable coefficients only of second order, not higher than the second order. That's what we have it in our syllabus, and higher order actually we don't have it in our syllabus. Now if I ask one question, so here actually I explicitly stated that these constant values actually it could be only the functions of x. Can I say that it may be a function of y as well? X and Y together. Can I say that? Yes or no? No, right? It is no. Why? Because if these are functions of y also, then we are calling that as the nonlinear equations. Got it? So we have linear equations with constant coefficients, linear equations with variable coefficients, but nonlinear equations actually we don't solve for higher order. But nonlinear equations, in case of first order, we solve it. Whatever the equations we solve in the first order are all are nonlinear equations on mostly, right? Here the linear equations with constant coefficients with variable coefficients, meaning purely the functions of x. So that actually explicitly you have to note it, right? So with variable coefficients, meaning it has to be functions of x only, functions of independent variable only. It should not be function of y. Right? So this is about the type of a differential equation what we are going to handle it. Now supposedly the first case we take it the constant coefficients. So if it is the constant coefficients, and usually we solve the second order differential equation. Right? So why second order differential equation is it is a more generalized equation. As long as actually you have a methodology how to solve the second order differential equation, same methodology can be extended. So the methodology what we are going to use is the factorization. So how we are going to do the factorization is, suppose actually we take the differential equation a into d square y by dx square plus b into dy by dx plus c into y is equal to f of x, right? So first actually the steps that are involved is, first is we will have to write the auxiliary equation. What is auxiliary equation is, first we have to note the convention. So the convention is, so capital D is used to represent d by dx. So wherever we wanted to operate the derivative d by dx, then that actually we just replace with d. So by keeping this, if you wanted to operate twice, so I wanted to operate dy by dx, again I wanted to operate dy by dx on this. And this is exactly in our standard convention, we call this as a d square y by dx square. But if you notice, if you simply call d as d by dx, d operated on d of x, so d of y, right? So d operated on d because capital D is dependent d by dx, and this is just the convention. Now if I simply call this as the normal multiplication d square operated y, this is exactly as if like d square of y. Got it or not? So these two are actually more or less similar if you follow this convention. Got it or not? So the normal multiplication of d with d again implies that taking the derivative of derivative. So if you multiply d cube, so that is d cube means 3 times the derivative. D power n means n times the derivative. So the normal multiplication implies that operating twice. Got it or not? I hope you understood this. This is a very, very important convention, right? So that satisfies. So that means d can be used as if like it is the normal multiplication. So as if like it is the simple normal multiplication without having any deficiency. So what we can do is, so ad square plus b into d plus c operated on y is equal to f of x. So cy and b into d of y and a into d square of y. So that is d square means d square y by dx square, d by dx into b, and so c into y is equal to f of x. So this is another way of representing the same equation. Now what we have to do, So first actually we take only the system dynamics alone, that is the complementary function. Alone to calculate, make the source function 0. So that is right complementary function. Right? How we are going to do it? So this is AD square plus BD plus C of Y equal to 0. So we made the right side portion as 0. Now what I will do, I wanted to factorize this. Right? So how do you factorize this? We know that actually if AX square plus BX plus C equal to 0, so if it is equated to 0, then we know how to find out the solution. This is x is equal to minus b plus or minus square root of b square minus 4ac by 2a. And we will get two roots, and let us call this as alpha comma beta. Right? Alpha comma beta. Then actually, so x minus alpha into x minus beta equal to 0. So that means ax square plus bx plus c equal to 0 can always be written as x minus alpha into x minus beta into equal to 0, because x so alpha beta values are decided by minus b plus or minus square root of b square minus 4ac by 2a. I hope you know this, right? So based on this understanding, this portion can always be written as d minus alpha into d minus beta of y equal to 0. Can I do that? Understood? Right? Now actually, so we got to this conclusion with the normal, as if like actually x square means x into x, it is as if like d square, d operated on d. So the derivatives are converted into as if like it is the normal algebraic polynomial. So this is exactly what we do it. Now actually, we don't know how to solve a second order differential equation. Till now, whatever we have learned is only the first order differential equations. Now, how to solve the second order differential equations? We use the same methodology, whatever we used in the case of the first order differential equations. We will extend that concept to the higher order differential equations. So for that, what we do, I'll replace, I know how to solve only the first order differential equations. So hence I will replace with another variable z, this entire thing. That is d minus beta operated on y if I equate to z. Then d minus alpha of z equal to 0. So this is the differential equation I need to be solving. Now this is dz minus alpha z equal to 0, or this is as if like dz by dx minus alpha z equal to 0. Don't you see that actually this is the first order differential equation? Got it? So we have arrived at a first order differential equation. I know how to solve this first order differential equation. So this actually, you can use the Leibniz equation. Anywhere right side portion is 0, you can even do even a simpler way. So dz by dx is equal to alpha z, right? Or it implies dz by z is equal to alpha into dx. Then you can integrate on either sides. So log z is equal to alpha times of x plus c, right? Or this can be treated as z is equal to e power alpha x plus c, or z is equal to e power c, e power alpha x, or z is equal to some constant a into e power alpha x, where a is the arbitrary constant. Got it? So we have got the z value as a into e power alpha x. Now this z value we will use it there, and because actually we have assumed that d minus beta of y is equal to z. This value we will reuse over there. Got it? So do you have any questions till now? Any questions? Right? Okay. So d minus beta of y is equal to z. So d minus beta of y, and we assume that this is z, and this z value is coming out to a into e power alpha x, right? Or this is dy minus beta y is equal to a into e power alpha x, or dy by dx minus beta y is equal to a into e power alpha x. Right? Now, this is again a first order linear differential equation, which is the Leibniz equation. The integrating factor for this is e power minus beta times of dx integral. So, this is e power minus beta times of x, right? So, this is y into e power minus beta x is equal to integral a into e power alpha x and e power minus beta x plus some other constant c. So, this is y into e power minus beta x is equal to, so a is a constant, e power alpha minus beta times of x, e power alpha minus beta times of x into dx plus c. So, y into e power minus beta x is equal to a into, so e power alpha minus beta times of x divided by alpha minus beta plus c. Now, e power minus beta x, we will take it on to other side. So, this is y is equal to a by alpha minus beta into e power alpha minus beta plus beta times of x plus c into e power beta x. So, y is equal to c1. So, beta will cancel, e power alpha x plus c2 e power beta x. Got it? Understood? Right? So, this entire thing actually I assume as a constant, which is an arbitrary constant, which is equal to c1, and this c I replace with another arbitrary constant c2. So, anyway c1, c2 are the arbitrary, you can simply replace with any arbitrary constants. Clear? Understood or not? Any questions on this? So, this is exactly is the methodology what we are going to adopt in case of identifying the complementary function. So, if you notice, there is nothing new actually we learned. We extended the same discussion of the first order linear differential equation even to solve the second order as well. Right? Now, you tell me, so here actually we are assuming the arbitrary constant as a by alpha minus beta. What if alpha equal to beta? If alpha equal to beta, then what happens? Can I adopt this as the solution if alpha equal to beta? Yes or no? Because in the denominator it is coming out to be 0, right? Obviously, you cannot adopt that as a solution because the denominator is coming out to be 0. Then, how can you identify the solution if alpha equal to beta? So, exactly follow the same procedure and try to identify the solution if alpha equal to beta. Or can I say that if alpha equal to beta, c1 plus c2 e power alpha x, if alpha equal to beta, can I do this? Yes or no? Can I say if alpha equal to beta, c1 plus c2 times of e power alpha x, can I call this as the solution? That is the question. Yes or no? Right? We cannot call this as the solution because this can be replaced with another arbitrary constant. But we are trying to solve a second order differential equation. Obviously, we are expecting two arbitrary constants. So, c1 plus c2 will become only one arbitrary constant c. So, that is the reason we cannot call this as the solution in case if alpha equal to beta. Now, you calculate if alpha not equal to beta, we have identified the solution. If alpha equal to beta, then how can you identify the solution? Can you try to adopt the same procedure and derive if alpha equal to beta, then what is the probable solution? Make it fast. You do it now. Done? Anybody got it? So the same procedure actually if you adapt it, so this is d minus alpha into d minus alpha of y is equal to 0. So if you call this as z, so this is d minus alpha times of z is equal to 0, or dz by dx minus alpha z equal to 0, or dz by z equal to alpha times of dx. You can integrate it. So this is log z is equal to alpha x plus c, z equal to e power alpha x plus c, or z equal to some constant a into e power alpha x. So this is the first solution. And even the second solution also it will be the same thing. So d minus alpha of y is equal to z, which is equal to a times of e power alpha x. So this is dy by dx minus alpha y is equal to a e power alpha x and you can identify the integrating factor again. So e power minus alpha into dx integral. So this is the integrating factor. So this is e power minus alpha x. So y into e power minus alpha x is equal to a into e power alpha x into integrating factor into dx plus c. So these two will cancel. So this is ax plus c is y into e power minus alpha x, or y is equal to ax plus c e power alpha x. So these two are the arbitrary constants. Our standard convention is c1x plus c2 times e power alpha x. So this is the solution. Actually we will get it. Got it? C1x plus c2. It is exactly the same procedure actually we followed. Now suppose if the roots are actually complex conjugates, because quadratic equation roots can be three different variations. So one is, so roots real and unequal, and the second one is roots real and equal. Third one is complex conjugates. Right? So these three variations. So this actually we proved this is c1 e power alpha x plus c2 e power beta x. And here the roots are equal, c1x plus c2 e power alpha x. In the third case, so even if it's complex conjugates, these are actually two different types of roots, two different roots. The meaning of it is alpha not equal to beta. So, but alpha can be complex constant, right? Alpha and beta can be complex constant. That means suppose if alpha equal to a plus ib and beta equal to a minus ib. Anyway, alpha is not equal to beta because the imaginary part is different. So it is the same solution we can adapt even for the complex conjugate roots. That is c1 e power a plus ib into x plus c2 e power a minus ib into x. And this is the value of the y value. Right? Now this actually we can expand further. What we can do? E power ax is there common. So e power ax we can take out common. C1 e power ibx plus c2 e power minus ibx. Right? And we know from the Euler's equation, so e power I theta is equal to cos theta plus I sin theta, and e power minus I theta is cos theta minus I sin theta. Right? So these values actually we can simply replace it here. Y is equal to e power ax into c1 cos bx plus I sin bx plus c2 cos bx minus I sin bx. Right? And if you further simplify it, so y is equal to e power alpha x c1 plus c2 cos bx plus I times of c1 minus c2 sin bx. Right? So this I will call as a simple constant a, and this entire complex value I will call as a simple constant b. So y is equal to a e power, so e power alpha x into a cos bx plus b sin bx. And this way we arrived at the complex conjugate roots as sine and cosine values. Got it? I hope you understood this. Right? Any questions on this? Right? So this is how actually we can find the complementary function for any particular integral value. Got it? Right? Okay. So I'll give you some assignment problem. You can try to solve it. So if you have any conceptual doubts, you can ask me now. Right? So note down these assignment problems. First one is d square x by dt square plus 5 dx by dt 5 dx by dt plus 6x equal to 0. In the second one, given x of 0 is equal to 0, dx by dt of 0 is equal to 15. Given x of 0 is equal to 0 and dx by dt of 0 is equal to 15. So this you need to solve it. And the second one is d square x by dt square plus 6 dx by dt, d square x by dt square plus 6 dx by dt plus 9x equal to 0. And d cube plus d square plus 4d plus d. D cube plus d square plus 4d plus 4. D power 4 minus 4d plus 4. D square plus 1 whole cube. D power 4x by dt power 4 plus 4x. Right? So you can solve all these problems and as assignment, and you should be able to solve all these things. Got it? So Nidhi, actually what is your question? So in the very first equation, you mean to say that, so that is the circuit element, right? So that is di by dt plus v by dt plus r by l times of I is equal to v by l. In this actually we have got the solution. I is equal to, so v by r plus c into e power minus rt by l. So is this the one you are asking? Reducible in Clairaut's equation. Okay. So what is your question in that? How do we get to know about substitution in very, okay. So how do we guess? So that comes only by practice. There is no other way. So you need to think. So in multiple ways and finally arrive at how to identify the variables, what needs to be done. And so many of the times if you people might be asking, this comes only by experience, right? There is no hard and fast rule to guess. It will come only by experience, because if you know all the methods, actually you will try to think in multi directions and finally come up with a solution, but there is no rule. Got it? So I'm sorry to say that there is no rule for that. It comes only by practice. Fine, so that's all. Yeah, thank you.